The topic I'm dealing with today is hydromechanical coupling and slope movements. Now, this is a topic that I've been really interested in and has underpinned most of my work in the last at least 30 years, although a lot of the background from my 48 years of working has been brought together into what I'm going to present today. It's based on two keynote lectures, one from 2007 and the latest one from 2020. And again, they're trying to bring together the body of theory and practice as it relates to these elements. So in soil and rock environments, I believe you can't effectively manage any excavation unless you understand the slope movements and what affects those. And there's a continuum of movements, obviously, from very small elastic deformations right through to collapse. And those movements are nearly always of sufficient magnitude to change the physical properties. And therefore, they also change the groundwater. And there's an impact also from external loading events. So that understanding of the mechanisms and the roles, stress, creep, instability, ground and surface water, through that movement process are pretty fundamental for the effective management and control of slopes. And that's really what we're about when we're doing any excavation. We're really trying to control the slope such that it remains manageable. So today I'm addressing the theory and practice of excavated slopes in a range of geotechnical settings and really focused on those water interactions, hydromechanical coupling. There's a number of inherent difficulties in that. Grasping the magnitude and the significance and the relevance of the effects when they do occur is, from my experience, difficult. But probably the most fundamental hurdle is the realization that any excavated slope is new. The environment doesn't change pre and post excavation, but that new slope that's constructed, it'll behave in a certain way that's often very difficult to predict ahead of schedule, before you've excavated it, and then the interactions that are going to occur through that process add that degree of difficulty. So how those impacts affect the newly excavated slope and the resultant slope performance then comes back to what geotechnical setting I'm dealing with. And that's a combination of stress, the modulus of the materials, their large-scale geotechnical character, the defects and the joints and cracks that are contained within the rock mass, and lastly, the defect characteristics themselves. So today I'm talking about reviewing the general state of the art in understanding movements and the interaction between water and deformations. We'll deal with the theory of hydromechanical coupling, the interaction of pore fluid responses, both in structure and masses, and how they affect the excavated slope. We're going to look at the hydrogeological cycle because it's really important to understand the context in which this new slope is being formed. And then we have to cover a couple of things, water-related things, looking at transient and partial pore pressures. And I'll deal with some theory on both of those aspects. And then I'm going to present to you my system for understanding and classifying slope movements. I have to do this every time because if I'm predicting ahead, unless I can thoroughly understand it and put it within a context, a framework where I can judge all those different elements, then I can't effectively predict ahead. And there's a number of practical examples that are going to follow on from that. So at the start, there's 5 basic concepts I'd like you to grasp. Firstly, all geotechnical materials are part of a continuous spectrum from soil to very hard rocks. They all behave according to the same engineering principles, and the differences are only a function of degree rather than fundamental nature. again, emphasising that fact that we have a new slope that hasn't experienced the environment in which it's being excavated. And all slopes move. Some slopes move episodically or continuously. And as that movement happens, then the likelihood of a hydromechanical coupling increases. And that can have negative or positive impacts. But that always changes through the lifespan of those movements. In a lot of cases, we end up with progressive failure. Movements start generating, they spread more widely, and maybe over the period of weeks, months, years, we get that progressive failure develop. So in some ways, I'm often not interested in the factor of safety because we end up with a hydromechanical coupling, and that means that there's a high probability of some adverse impact in the future. So this leads to the final aspect of those 5 basic concepts: management. I often say now, I'm not designing slopes, I'm managing them. And the success of that really depends again on how well we understand hydromechanical coupling and what happens through the life of the slope. So firstly, let's start with the earth. We're excavating these slopes, these new slopes, and they're porous. They've got holes. So the slopes and the groundwater that's contained within, and then any water that's introduced from external sources such as rainfall, runoff, they're interlinked in their mechanical effects on each other. And that's hydromechanical coupling, the physical interaction between the hydraulic and the mechanical processes. There's a number of examples that I'm going to cover in this lecture. Firstly, pore pressure responses, then the geotechnical setting and how that impacts on the process, the interaction with external water sources and how that impacts on slope failures, unloading and pore pressures, and then the role of undrained loading and liquefaction potential, where we get very large post-failure deformations that nearly always have very adverse outcomes. So the key aspects for understanding this hydromechanical coupling, that the behaviour of the soil and rock defects, they change due to the changes in normal and shear stress that occur as we excavate the slope. That change impacts on apertures, the width of the cracks, and as they change, the change in the hydraulic conductivity or permeability of the materials we're dealing with. There's a very large sensitivity to defect apertures, and that's one of the key messages about hydromechanical coupling. And we have these different characteristics, hydraulic characteristics, depending on whether we're dealing with soil or the different rock masses and all the geological processes that have impact on those. And then stress also plays a role. And then lastly, we're looking at the relationship between hydraulic conductivity or permeability and depth that occurs naturally and also as a result of the excavation process. So let's start with some simple theory. So the very simplest theoretical example is effective stress. So our effective stress is equal to the normal stress minus the pore pressure. If you really want to understand effective stress, I've got a little experiment for you. You get into a bath full of water. You stay in the bath and you pull the plug out and you don't move until all the water has drained away. That will give you a very clear understanding of effective stress. So pore water controls deformations, and the deformations, they affect the pore water. It's interactive, a two-way process, dynamic, and affects excavated slopes and the groundwater contained within. So let's look at a bit more theory here. We've Now I've got shear stress versus normal stress. For a test sample, you can see at the top here, a test sample with a major principal stress and a minor principal stress. There's a confining pressure. And we have two envelopes, one for sliding on a structure, a defect in the rock mass, and the other for the failure of the rock mass. And then we have our Moore circle. This is in terms of sigma 1 and sigma 3. That's the inherent strength of the rock that we're dealing with. The mu here is the pore pressure. As we add water into the system, we slide this semicircle to the left until it touches either sliding on the surface or sliding of the rock mass. And obviously, with transient pore pressures, as this changes, this cyclic process can continue through the life of an excavated slope. Now let's deal with groundwater. We normally talk in geotech engineering about groundwater hydrology, but groundwater is also covered in soil mechanics. In terms of groundwater hydrology, it's usually about provision of water from aquifers or dewatering of an excavation, and the simple transmissivity, which is the permeability times how thick the aquifer is carrying that water. But then the other factor is also storage coefficient, so the quantity of water that we can take out per unit drop in head. In soil mechanics theory, we term that consolidation, and we use the term CV, coefficient of consolidation, which controls the time rate of dissipation of that pore pressure in a transient system, one that's changing with time. But the concepts are identical. The concepts of groundwater hydrology and soil mechanics consolidation theory are identical. The same concepts apply. And you need to use that through your understanding of hydromechanical coupling. Now let's look at coupling and slope behaviour. As I said at the start, all slopes move. And they display a range of behaviours. And this simple little strain time model here shows how we have an elastic strain on first excavation, then that settles down over time. It can go into this next phase, which is creep of the rock mass over time, and then then it can continue out of that into failure. Not all slopes follow that whole process. Some stop at elastic, some stop here and then never move again, but a large number continue on through creep and failure phases. There's 4 types of hydromechanical coupling. There's the direct and the indirect. And each of these I'm going to represent and explain in terms of a little square block here. This is a 3-dimensional block, and you can see I've got little cracks in that. It can be a block of soil, can be a block of rock. And in that block, I've got a little tube that comes out the side, comes up here, and measures different water levels, the triangles. So I've got an action that happens on the left-hand side, and I've got a result that happens on the right-hand side. So the action in this case is an increase or decrease in the stress, shown here by these 2 black arrows on top. I'm either pushing down on the block or I'm lifting off the block. And as I do those, if I push down on the block, that water pressure in that crack goes up. If I take load off the block, the water pressure in that crack goes down. That's type 1, direct hydraulic coupling. Type 2 hydraulic coupling is rarer, but still occurs. And that's where we actually change the water pressure that's in the cracks. And we get a volume change. As shown here, that square grows to a bigger square because we're forcing it apart with the water pressure. So the water pressure goes up or down exerts a force on that block, and we either get swelling or shrinkage as a result of that. Now we can go to indirect hydromechanical coupling, type 3. And again, there's an action on the left, a result on the right. Again, we're dealing with a change in the stress through to loading or unloading of the block. And what we find is we change the hydraulic properties of the cracks. We either open them up or we close them. And that's dependent on so we're changing the hydraulic conductivity, K, and the storage. The last type, type 4, is where we're changing the pore pressure in the system, delta mu, and we get a change in the mechanical properties. This is really important for large post-failure deformations. Impacts of excavation. So we can take that theory and put it into practice. And I've shown here a slope that's been excavated in a series of benches. And the geology is pretty simple. There's one block of rock at the top, which has a lot of cracks in it. Another block of rock at the bottom, which has a few cracks in it, those little lines. And there's a couple of fairly continuous structures through it, as shown here. So if we start with the left-hand side, I take this structure, which is dipping out of that slope, so area 1. If I change the effective normal stress by loading it, then I change the deformation on the structure itself. It squashes up. And the amount of squashing is dependent on the effective normal stiffness here. So we're changing the aperture, and therefore we're changing the hydraulic conductivity and the storage. I could also get shear. I could push the top of the structure over the bottom of the structure, in which case I'm dealing with the shear stiffness. And that also changes the hydraulic properties. Going here now to the rock mass. So we've looked at the structure, now we'll look at the rock mass. And over here, we've got a change in the confining pressure, which is back to our simple definition at the start of effective stress. We can have a volumetric deformation, either positive or negative. And in this case, you can see from these arrows that as we excavate the slope, it moves out to the dashed line. So we're getting a volume increase. And in this case, the positive volume change is dependent on the drained bulk modulus of the materials. We can also get some shear generated, in which case the shear modulus will impact on the response. Now, what does that look like in practice? Well, here we've got point 1 down here where the structure dipping out of the slope, and you can see the top of the excavation is sticking out above the bottom, and you can very clearly see the apertures developed along that whole structure. Go to point 2, where we've got a fault, so quite a continuous structure in the boundary between the very jointed rock mass and the poorly jointed rock mass. And again, you can see the aperture that's generated from the dilation. It's a shear movement in a toppling mode, and it's related to just bulk movement of the whole mass as we excavate. But the result is this dilation. Now, the impacts of excavating materials can be very large. People often don't realise how large they can be. This is an example of some modelling we did for a very large excavation, 800 metres deep. Excuse me. But the deformations, the distance they've changed is up to 700 or 900 metres away from that excavation. So don't ever be fooled and think things are just happening very close to the excavation. Depending on the setting, and there's 2 different geotechnical settings, one at the top here and one at the bottom. It's 2 different rock masses. In this rock mass, it's only 80 metres. In this rock mass, it's 700 metres. So the hydrogeological concepts that we're dealing with. So it's also always important to understand that setting in a wide context. And I've used an example here of an open pit because it captures many elements of the problem and the issues. Firstly, we have a surface water catchment. So that's where we collect rainfall. And that's driven by the topography around the structure of the excavation itself. Separate to that, there may be a groundwater catchment, which you can see here is much larger than the surface water catchment because the groundwater level is rising up behind that. So this rainfall that's happening from the surface water catchment, the precipitation gives us runoff, infiltration through the upper materials, infiltration through the near surface zone of the excavation itself. And a lot of that ultimately reports to the groundwater table at depth. And then we might have some other structures within that that hold water temporarily, like a sump in the bottom or on a bench. All of these elements can play a role in what's happening. And the next example I'm going to show you is what happens with transient water pressures developed from this precipitation and structures. And so we look at a slope and it looks like this. The slope is predominantly dry. There are a lot of defects in them, but only some of them have water. That's that transient response to a rainfall that's happened on this slope and has given us these hydromechanical impacts. Excuse me, just one more sip, I'm getting a little bit dry. So the groundwater table and pore pressures. Starting with some simple stuff, we have the saturated on the left here in example A. Under the water table, we have a capillary fringe where water's sucked up, and then we have the unsaturated zone. We'll ignore the capillary fringe. The next thing we deal with is moisture content. And you can see there's still moisture in the water, in the materials, even in the unsaturated zone, but it's not until we get to the capillary fringe or the water table where we're fully saturated. That's 100% of the pores or the cracks in the ground are full of water. That's represented over here again by this tube, which has little tubes that I'm representing as piezometers coming out of it. And you can see here in this little area, we've got some water, the shaded zones in the cracks, but they're not completely filled. And then we go below that and we've got completely filled cracks. And that pressure head then through that profile looks like this. It's negative above the water table and then 0 at the water table and then increasing below that. Now let's deal with transient and partial pore pressures. And again, it's the same system. We're going from left to right. So we're dealing with a profile on the left that has unsaturated zone and a saturated zone. And we've got these 4 little tubes poking out the side to represent what the water level rises to, or the pressure at each of the ends of those little tubes. In this particular tube, we've got vertical flow happening, which means the pressure at a higher elevation is greater than the pressure at a lower elevation. Now that's partial pore pressures. Let's move to the next example here, where we have the axis of pore pressure versus depth in that tube. So here's the water table, the boundary between unsaturated and saturated. This is the transient pore pressure response. Water entering the ground surface up here gives us this pressure here over time. And then we end up with, below the water table, hydrostatic pressure, which is the same pressure you feel if you jump in a lake, you jump in the ocean, you jump in a bath. And the pressure's half the weight of water, half gamma W times the height squared. But as I said before, we've got vertical flow in this instance. The lower pressure is less than the higher pressure, the higher level pressure. So we can also have partial pore pressures. The ground is fully saturated, but you can see this pressure distribution as represented by the triangle is probably only 55% of the full hydrostatic condition. So we're often trying to achieve partial pore pressures in excavating slopes. Now we come across to the right-hand side. And we've got the same sort of system. We've got piezometers at the same elevations as for the tube on the left, and we're measuring what happens over time. So our pressure head here starts as negative at the ground surface, goes to 0 at the water table, and then becomes hydrostatic below that. Over time 1 through to time 5, when the infiltration from rainfall starts, we start generating these curves of pressure, which eventually become positive and have this form until they ultimately lead to also an increase in the groundwater table at depth. So these are time-dependent transient pore pressures developed during rainfall periods. What does that look like? So here's a slope, and let's look at this for scale. That's a four-wheel drive down here, and over here's the front end of a grader, road grader. Look at the rain on these slopes. We actually can't stop the water getting in. That's why it's important. That's why hydromechanical coupling is important. This is a 240 mil rainfall event. Look at the water flowing here. That's a one-day rainfall. And where do we find it? Predominantly down the structures. So it's getting into the major continuous structures, but it's also getting into the minor structures, as you can see here, flowing out of that crack there. You just imagine what impact that's having on transient pore pressures below the ground and the deeper groundwater table. Sometimes we create problems for ourselves. A big flat area, no drainage, there's clouds there and it's raining all the time. Again, we're going to get transient pore pressures developed as a result of this that are eventually going to make their way to the deeper groundwater table. We also have to think about catchments. Are we actually making things worse by directing water to the wrong spots? So if we look at the top here, we can see all of the water that's on this flat area up here flows down to the front of the slope on the right-hand side. It's caused this failure here. As you can see, the water running into it. And when you look at the structure that we've got here with a subvertical defect and a flat dipping defect dipping out of the slope, it's very easy to imagine how this structure, which is very sensitive to stability in a stability context, would be impacted by that water pressure getting into these cracks. Now let's look at something else. The differences in rock mass character. Now, I believe you can fundamentally look at a rock mass and say, I think this is what's likely to happen in this rock mass. You won't know the amount. You can't predict that accurately, but you can understand the direction in which that's going to go. So the hydraulic response in this rock mass is going to be completely different, as you can imagine, to the hydraulic response in that rock mass. More widely spaced joints, probably more open, higher aperture, higher hydraulic conductivity. Again, we've got an example of rock mass character. It's a very jointed rock. We can see here the average block size might only be 50 millimeters, very closely spaced joints. But there's apertures due to the excavation process. Sometimes they're hard to pick up, but they can be very fine, as shown here on the small cracks. They get larger as the cracks get bigger, and very large when the cracks are very long, when they become closer to first order structures like shears or faults. That leads us into the next slide, which really talks about geotech setting. This is a slide I prepared, or a diagram I prepared to illustrate the general hierarchy of structure in soil and rock masses from 1 to 5. And we're dealing with joints to very jointed rock masses, contacts and bedding, foliation, schistosity, alteration, shears, faults. And these are all numbered up here. And they're impact on hydromechanical coupling and on slope deformations obviously increases as we go from left to right. So understanding that basic geological hierarchy of structures and the importance for this topic is fundamental. The next thing is, as always in engineering, we must be able to place what we're doing in the concept of scale. So what we might be worried about on something that's 10 metres high might be the little cracks. We go to the next scale and we've got the next hierarchy of cracks that are important for that response until we get to the overall slope as shown here, and we're then looking at the big structures, the faults, the bedding, shears, those sorts of things. So placing the basic understanding into the slope scale or the excavation scale is also a fundamental step in this process. Now let's look at in situ permeability. So this is hydraulic conductivity versus depth. This is what naturally happens. These are real measurements from below the ground of hydraulic conductivities. And there's a near surface zone, which in this case is 300 metres. I've seen it 400 or 500 metres sometimes. Sometimes it's only 100 metres. We have a decreasing permeability as we go deeper in the ground. So a reduction in the permeability, K, due to stress. So the rock on the sides or the soil on the sides presses in. We might have shear displacement, number 2, which leads to an increase in K in some instances. Precipitation or cementing of the joints and the cracks due to minerals coming out of solution can obviously decrease our permeability. And then lastly, at depth, there's sometimes a dissolution where we're actually taking it back into solution under stress and in a different temperature environment. Again, a change in the permeability. Let's look at a really large structure. And this is a regional structure that's exposed here. You can see there's 2 completely different rock masses. And I don't think that's that man's in accord with current safe work practices. But anyway, we needed to get some information. If you look closely, you'll see the aperture along that structure there. The structure itself looks pretty poor, very ground up. But there's still aperture. There's still a crack. And if you look at how wide those dark lines are, just compare it to the helmet he's wearing. Those apertures are probably 50 millimetres, at least. They're substantial. So maintenance of aperture, even on very large structures. And that gives us an anisotropy in the permeability, as shown here with those blue arrows. Clearly, it's going to be much lower permeability trying to go across that structure than it will along the structure, because we have these channels, these irregular channels that nearly always have a tortuous path that are in the plane of a structure itself. This is some work from the US Geol survey looking at nuclear waste storage. And they did this very careful investigation of an area with those 4 holes shown vertically there, investigation drill holes. And they came up with this model. And you can see there's some fine cracks, which are the light lines. And then there's some more continuous high permeability structures. And there were 4 main characteristics that you need to remember about structures. So often there's individual larger aperture open flow channels along a major defect like 1. Sometimes there's subhorizontal tension joints with evenly distributed aperture and flow. The flow is often also concentrated where we have a steeply dipping structure truncating on a flat structure or a subhorizontal structure. And then lastly, where we have intersections. These are all the typical higher flow locations. Now let's look at defect behaviour. We're going to deal with normal loading, shear displacement, the strain behaviour that happens, and the impact on transmissivity, which, remembering back, is our permeability times the thickness of the aquifer. So dealing with under normal loading, under normal loading at the top here, we have a normal stress and we have closure of the crack. So the crack starts closing as the stress goes up, as the load goes up, but then it reaches a plane and doesn't close anymore. So that means, when we look over here, that we do get a decrease in the hydraulic conductivity or the transmissivity here, but there is a residual that we can't do anything about. That stays locked in. We come down here to shear displacement. So when we're pushing one section of the structure over the top of another, and if we're dealing with a clean, rough joint here, these are the typical displacement patterns for either a small piece of drill core or an in situ block. And the in situ block has a shear stiffness, which then decreases back to the residual over time with strain. We don't get as marked a effect, sorry, for the drill core, is very prominent. We don't get as marked an effect as we have when we're dealing with a larger mass of structure. But that causes dilation, and you can see that under small shear strains, there's no dilation. There's actually closure to start with. So initially, we're not changing the transmissivity of the structure, either in the drill core or in situ, but then as we have larger and larger shears, we do start increasing the transmissivity. This is a very useful little tool I've found, and it's a plot of hydraulic conductivity versus joint aperture, so how wide the cracks are. It's a simple system here. It's 4 parallel structures, open a certain amount. This really emphasizes the importance of aperture. So if I have a spacing of 0.1, that's 10 cracks per metre of rock, that means I have an aperture of 0.1 of a millimetre, that's very fine. I have a certain permeability or hydraulic conductivity. If I have 1 joint per metre, I have the same hydraulic conductivity if I have an aperture of 0.22 millimetres. Aperture is pretty critical. So our permeability is a function of the cube of the aperture here. There's a fair bit of discourse about whether this rule applies, but it generally does in my experience for most cracks, apart from going down to very, very fine cracks. So keeping that concept that the aperture is the permeability is a function of the cube of the aperture is fundamentally important. Large-scale behaviour of defects on excavation. It's really important, the interpretation of this. So we generally get a bigger impact from a change in the normal stress than we do from a change in the shear stress. Hard rocks and clean joints, we get more aperture increase and a larger increase in hydraulic conductivity. And then as the rock mass modulus or strength decreases, the impact of those normal or shear stresses becomes less on hydraulic conductivity because the material's weaker. It crushes, forms gouge. It doesn't have a clean structure. And in general, when we have very large defects, so in the geological hierarchy, those ones I was talking about as number 5, right up the right-hand end in that model I showed you earlier, if we have any sorts of strength alteration or clay infill, then we're normally going to get a decrease in the hydraulic conductivity for flow normal to the event, to the structure, but an increase parallel to the structure. And that's what's shown in that next point. So back to the excavation, deformations and failures again. So concept that we're dealing with are possibly these 4 phases of movement: primary displacement with time, secondary creep, tertiary creep leading to collapse. And some slopes don't go through all those, they just have a primary movement and then become stable. And that's back to this more circle envelope, our failure on a rock mass and sliding on a structure. So we're taking our Moore circle here, we're adding in transient pore pressures, and we're sliding that Moore circle closer to either the sliding strength or the rock mass strength. That's what happens along this process here and during hydromechanical coupling. There's a fair bit of research on natural slopes, but that's very useful for us because they recognise that displacement rate over time has all of these phases, starting with creep, post-failure, occasional reactivation, then active landsliding. But we need to think about the mechanics that we're dealing with and that's governing behaviour, and also the moisture content changes. So we start here with an initial rock toppling failure and rock mechanics. We're increasing the moisture content as we go through this. Move on to soil mechanics. The collapse has occurred, there's a big pile of debris, so we're dealing with soil mechanics here. And down we go, lastly we come to fluid mechanics, when we've got very high moisture contents added into the material and very high nominal rates of movement, 10 metres a second. So it's very difficult for us as geotech engineers to actually get these boundaries very right. So this prediction process is pretty tough. Categorisation of slope movements, I usually think of them, these 4 types. So we have a progressive movement leading all the way to collapse. We have a regressive movement that goes through a series of short-term decelerating cycles going to stability. And then we have ones that are transitional, type 1, and then moving on to collapse. This is the ones we're dealing with. I also think there's a stick-slip type movement in embedded structures. It's pretty powerful as an educative tool, but I think it's quite limited. It really doesn't capture all the acceleration times. Implies that this is happening over a long period, so you have a lot of warning. Doesn't capture all the movement patterns either, from my experience. And so I've come up with this system. This is how I classify things. I think of pre-failure movements, I think of collapse movements, and I think of post-failure. Up here, it's important for me to understand these patterns of movement because it's in this zone that we can manage things better and perhaps stop it getting to the next one. And that's really part of the aim. Once we get to failure, we've got a whole series of type behaviours that can happen, but sometimes it can be very minor acceleration. We don't always have that long acceleration, that long warning time. And then once it has failed, one of the things we do have to do as geotech engineers is say, is it just going to stop? Or is it going to keep going and do some very large damage? We have also a classification system. Now, I won't go into this in a lot of detail. And this is what I use for managing slopes. These divisions up here, because they're related to the sensitivity to the environmental factors. These tables are in my keynote addresses, which will be available later on. And that sensitivity at very low creeps is very low, but as we keep getting faster and faster rates of movement, we increase our potential sensitivity. People often look at the magic number. What's the maximum velocity per day that things could move at before collapse? They're looking for the holy grail. Really, you can see from the range of numbers here that you can't actually have one number that fits all geotechnical or geological conditions. And so I think this is really a bit misleading, and I'm very uncomfortable predicting things like this any more than a couple of days ahead. So just summarising what that means now, we have increased or decreased sensitivity to the environmental factors. As we move the slope over time, we have increased potential for large post-failure deformations because we're increasing the hydraulic conductivity, moisture content, the infiltration capacity, and the responses to rainfall. So as we go through those 5 phases from elastic, creep, cracking, collapse, post-failure, this is what's happening potentially in our environment. Let's have some examples now. A layered soil context. I'll go through these pretty quickly. This is a soil slope. The materials are only 250 kilopascals. As you can see from this very sharp corner here, they're excavated at about 42.5 degrees, 35 metres high. This slope has a series of structures here that are in this Torella sill, and they're open joints. So what role would they play? There's also another series of structures in the upper zones here and here. So this is a trial excavation that was excavated from over time, and these are the days from 146 through the end, 245 days. We're going to look at the movements that happened in plan and section, starting on the left-hand side. So first off, we dewatered the material for a long period of 140 days, and the whole of the ground settled. Then we did some excavation, as shown here, and we had rebound. The ground all came up. And there was also some shear taking place below the base of the excavation. It's only small, but it's happening. The next phase, we dig a bit deeper into another unit, and now the rebound relaxes and it starts falling again. And we get some more shear. This was a slope that was designed to fail. What we wasn't expected was that it would start failing all the way through the process. So bits started falling off. As we dug a bit further down and intersected this continuous structure here, we had this part move back. The ground went back up again because the front of the slope fell off. We go to the next phase, and we've done a lot more excavation now, and we get a little more shear happening, and this part of the slope wants to go down, and this part of the slope wants to go up. So it's almost a circular type failure. Lastly, just pre-failure, we no longer have any shear. All of the front of the slope wants to fall off. And then finally, we had the collapse happening, and a tension crack formed way back here, and this part of the slope went up because it was no longer being tugged down. Now, in plan, what that looked like through those various times was that initially, this is a plan view of that crest. So this crest just here. As it was excavated, surprisingly, the slope wanted to move in this direction. Then over time, it started moving in that direction. And then finally over here. And this direction was related to those open joints I talked about. So geological structure, in situ stress, the different geological units, the role of structure, continuous structure, all played a role in what is a complex system. I was lucky here because I had a lot of monitoring, so I could fully understand what was going on. But these are the processes that are happening in all slopes to a lesser or greater degree. And there's an impact on water here. We can see some water profiles, and near the trial slope itself, we can see that shear has actually stopped depressurization, has allowed higher depressurization. Less depressurization, because the shear on the structure decreased the hydraulic conductivity normal to it, like I explained a bit earlier. Now let's look at the dip slope. This is a slope that was in 4 years of design life, very small amounts of movement, maximum 200 millimetres. But then after about 3 years of wet seasons, we started getting these responses to groundwater and in the piezometers, until we ended up with one of these direct couplings for a rainfall. So the various types of movement happening on that slope. But the one thing I want to point out is this is another slope, a different one, but this cross-hatched area is the area that eventually failed. But the actual failure started here in June 1992. Then it got slightly bigger in July, a month later. And then a different part of the slope moved in November 92. And then September 92 here. And then finally, we had the slope collapse in April, May 93. So progressive failure. We're not failing the whole slope at once. As this part moves and goes beyond peak stress, peak shear strength, it sheds its load onto adjacent parts of the slope. That's what the cracks look. See the aperture here. If it rains here, you can't stop the water getting in. This is a very good example because I'm going to show you what happens as we take off 3 layers of rock here in a layered strata. And these are little piezometers like we've seen before, little tubes, and the triangles are the starting water level near the surface. We take off the first layer and we get a reduction due to unloading. Remove the stress, the pore pressure goes down. No changes out here, even though we've got small movements, as shown by the red arrows. We take out the next layer, layer 2, and we've got much greater movements happening at the surface and at depth. And we're getting reductions in pore pressure because we're getting aperture. It's starting to drain. As we go further to the final phase, number 3, we're actually getting the opposite. We've now opened the rock mass enough that the water level is now going back up to the surface. And that's when failure occurs. So remember this one always, 90% of all failures have water associated with them. So I've got another little example here where we've got a rock mass with structures dipping out of the slope at about 25 degrees. The slope's 30 degrees. And that's what it looks like. One part of the slope is very jointed, very blocky. And back to that geotech character, you can imagine its response to rainfall will be very different to this rock mass. Almost massive with some joints. And if we look at those 2 responses over time, the first example is clearly the water levels going up in the piezometers with every rainfall. And we have a failure. The second rock mass, the very tight one with very widely spaced joints, no changes to groundwater at all. Now let's look at another example here where we've got, again, a whole lot of structure dipping out of a slope. Sorry, it looks like this. A volcanic over a shale, dipping this way with a very major fault zone at the bottom. So geotechnically, it's pretty bad. Structure looks like that, which is pretty bad as well. So let's look at what happens over time through each of the wet seasons. And this is movement, displacement vertically with each cycle of the wet season. And as we can see, the responses each time are increasing. That's the hydromechanical coupling. Now let's look at some examples of what happens with, this is one particular project I dealt with. They had over 100 failures. And I'm showing the data from 84 of those and a whole range up to 200 metres high. And what was the evidence about rainfall interaction with those failures? So we had rain on the day of the failure itself and then rain on the previous 7 days. So we generally need to saturate the material, and then the worst case is when we have saturation of the material and rainfall itself on the day, a significant rainfall event. Lastly, we're going to look at unloading. We're getting very close to the end now. And here we've got an example where we might actually have ground surface here, an initial water table here, and we dig this slope. We excavate it. And we've got another piezometer in here, and depending on the pore pressure coefficient, which is the measures the response of the material to loading or unloading, the measures of the response of the water in the material to loading or unloading, we can have various pore pressure responses in that. And this shows you over time how, as the slope is dug and before the new groundwater table forms, that at this location, we generate a negative pore pressure because we've taken the load off, and then that slowly dissipates over time. So if we take that slope I showed you earlier, and this is where the water table is still recovering, so that was a fully dewatered slope, but this is the impact of water. If you take a slope that has water like that, and you form that, steeper, that's an example of indirect hydromechanical coupling type 1. We're unloading the slope. We do have some dewatering in place as well, but we're unloading the slope. These are soils, and the materials have gone into negative pore pressure because of that. And that's what's holding the slope up until we turn off all the bumps. Next, I'll deal with liquefaction. And this is an example of a job I did more than 20 years ago. The Thredbo landslide in 97, and 18 people died here. So this is an example of hydromechanical coupling type 2 and 3. It was only a very small mass, 1,300 cubic meters. It's just a few truckloads. But there are actually two slides, and you can see them here by the brown masses. There was a water pipe up here that saturated this area. This area failed and fell down here, knocking over the upper lodge, ski lodge. But when it did that, it also fell onto an old peat bog behind the house, behind the lodge. And that caused this second failure, which swept down here. So undrained loading. So, and a liquefaction failure. So, how do you turn a rock mass like this into that? And again, you can see the scale down here by the buried truck and the buried drill rigs. And I think only one person was killed in this particular instance. But it almost looks like the material is still flowing, but it's not. So just some closing statements. I'm not going to close with any conclusions or a summary. Most of the detail I've given you here today, and even more, is contained in the two keynote lectures from 2007 and 2020, and they're available on request. But there's a couple of important messages I'd like to leave you with. I trust, firstly, that you've appreciated that to effectively manage any excavated slope, we need that exquisite blend of science and engineering. We need to integrate the science disciplines, geology and hydrogeology, with rock mechanics and soil mechanics. And the key skill for success is being able to, I believe, break the problem down. What are the different technical aspects? Prioritize and then identify those factors. And I always conceptualize the influence of each in simple terms. And then I bring it all back together again, a model that represents everything that's in the ground. And lastly, this is something I've learned throughout my life. Accept nothing, question everything, and always go back and think about things. Thank you. And questions, and they can be in writing if you wish. If you send them through to the mailbox address just there,